And start. Hello and welcome back to Calculus 3, officially, right? Section 13.5, triple integrals in cylindrical and spherical coordinates. So, in the past, you learned about polar coordinates, which helped you with 2D domain. So you learned that you can find the area using x, y, which was rectangular coordinates, and then using r, theta, which were polar coordinates. So now the split goes this way. For 2D, you start with the x, y, and then you upgrade that into 3D as the x, y, z. In the other realm, you start with r, theta, which is polar, for 2D, and then you go r theta z, which is cylindrical, and r theta phi, or r phi theta, depending on which way it's written, spherical coordinates. So there's that. Now, both of these systems are developed to deal with round objects. So the cylinders, like your the can for the soda can or something, and then spherical, anything that is, thank you for modeling, and spherical coordinates, obviously something that is ball. Now, parts of those are important, so we'll see why and how. So let's go and work on cylindrical coordinates. So clearly, word cylinder is in the root of the word cylindrical, and a cylinder is, as I said, and as Jake modeled already, it's a soda can, right? Now, if you look at the soda can, you have the domain, which is a circle, and we can use polar for that domain, so r theta, and that domain is going to be r equals some number, not hashtag, r equals, I don't know, some number a. Pound sign? And theta is going to be in between 0 and 2 pi. And then you have the bottom to be z equals, let's say, 0, and the top z equals some value again. So as you are looking at this, right, you can quickly see that the integral, right, for something like this would be dealing with, again, polar coordinates and then enhanced by z. So what do I have? I have the region D for some function f of x, y, z dv. And here is the integral now. So we start with first that your f now is no longer x, y, z, but it has to use the conversion from rectangular to polar. So x is r cosine theta, and then r sine theta, and then z. And then we have r dr, oh sorry, dz first, dz, r dr d theta. I still have to put the limits in, but this is the formula. Now our outer integral is theta, so angle, so alpha and beta. Our inner integral is a radius, so that's going to be some kind of function g of theta and h of theta. And finally, capital G of r cosine theta, r sine theta, and capital H, r cosine theta, r sine theta. Now you're probably freaking out. What are these limits? Guys, just r cosine theta, that's x. right? And r sine theta, that's y. So that's g of xy, written in polar, right? In polar form. So for those of you struggling with these conversions, we have that x is equal to r cosine theta, y is equal to r sine theta, and z equals z. So that is our conversion. And again, the entire reason for existence of something like this is to make life easy when you are dealing with a volume which is of a cylindrical realm. See, the issue that you have is that if you want to integrate a cylinder using rectangular coordinates, your domain is going to have the limits which eventually will have to use trigonometric substitution to solve. And that's annoying. So what we do is we bypass that calculation by using polar coordinates. So polar coordinates are in the base. That eliminates all of the trig sub stuff. And then you just have a z, which gives you the top, right? You can model that can one more time for everyone to see. So you see that this can, right, is straight up z. And it has the flat bottom and the flat top.
Is this thing on 4 dimensions?
Yes, it is 4-dimension because of the function in here. But if you take this function out, you are only looking for the volume of the can, which is actually the first problem I want to do. So let's say that we are looking at the can. We can also, here, right, that was a multi-dimensional now because we could also hear the can at the same time. I want to actually, I have this as a part of one of the project problems. You didn't get this one on your project, where you go online and you figure out the dimensions of the regular can and you're figuring out the volume of the can using the triple integral, making sure that the advertised volume on the can is actually the one that you are computing. Because if it's not, you don't have to go to school anymore. You learned enough. All right? All right. So let's see dimensions of the regular can. All right. So here are the dimensions. They say that the US standard can is 4.83 inches tall and has a diameter. So it has a diameter of 2.13 inches. Oh no, 2.6. 2.6 at the widest. 2.13. You see that the can is a little bit in, right, on the top. So wherever Jake is holding it right now, that's where it's 2.6. On top that it's kind of squished in is 2.13. So we're using 2.6. Thank you. All right, so my radius is 1.3, clearly. And my z bounds are z equals 0 for the floor and z equals 4.83 for the ceiling, or the top of the can. All of the units here are inches. I want to compute the volume of the can. I'm using triple integral. And since I'm using a triple integral, I'm not going to use any function in here because that will make it a 4D. So I'm only going to use the string, which is always standard, which is dz, r, dr, d theta. So you need to remember this as a unit. That's it. For the cylindrical coordinates, that's it. That's your string. You can move that r in front of dz if you want to, but that's the string. That's the order, and you must have that r because of polar coordinates. So that's the string. You are memorizing that string as is, and then you will do the limits now on the integral. The most inner integral is dz. We see that z goes from 0 to 4.83. Radius, well, r is going to go from 0 to 1.3, and we want the entire can to go around, which is 0 to 2 pi. And now we can calculate the volume, integrate dz, so we have 0, 0, 2 pi, 1.3, and then this is going to be 4.83 r dr d theta. Integrate now the r integral, that's going to be 4.83 over 2 r squared from 0 to 1.3, still d theta. Then we have 0 to 2 pi, this is 2.42. When you, it will be 415 and then, yeah, whatever. R cubed, so that's 13, that's 169, so that's times 1.69 minus 0, no one cares, d theta. And when you integrate this, you will get 2.42 times 1.69 times 2 pi. And this would be in inches squared. So that would be in inches squared. So let's see. Yeah, inches cubed. Pay attention. I'm trying to compute the numbers, so I want to get the decimals. It's engineering. 2.42 times 1.69 times 2 times pi, so 25.7. So volume is about 25.7 inches cubed. Now it's your, where you go look into conversion tables, you get the conversion tables to, there we go. Look into conversion tables to get the, converted this into ounces or liters or milliliters, whatever you want to convert. So that's the cylindrical. So that's that. Now let's take a look at some of the homework exercises which they suggest we should work on. So cylindrical integrals, guys, they are not issued. The spherical are the scary ones. So here is a nice nice problem. X, Y, Z. We are going to draw at 2 and then go down and then come up with this curvature over here, come up with the same curvature over here. And that's our shape. It's a half of the can. We have in this integral given as XYZ integral. Now look at this monstrosity. So this is what you have to compute. Really?
Are they giving us?
Yes, this is what's given. But
I thought you were just like pulling these numbers out.
oh yeah, this is all well known. It's obvious. It's common knowledge. All right, so this is a problem that is stated in a book, and you are supposed to integrate this. Good luck, right? Because when you integrate in Z, when you integrate this in Z, you are going to get number 2 on top. And then you are supposed to integrate in terms of Y, which would be some type of inverse tangent something. And then when that is over, look what's next. And that's going to be eventually trig sub. Yeah, so they give you all of them. Everything that you see over here is what you see in a book. Now, what is the way to do this? You are supposed to actually use the cylindrical integral, because this is the half of the can. So the only thing that is going to be different in this problem than what I did for the can up there is your limit for theta. You see your theta? Theta starts here on the positive x-axis at 0 and goes not all the way around. It goes how far? Halfway. So what are the limits? 0 to pi. The rest is the same setup. You have your radius 0 to 2. Well, I didn't write the 2, but it's 0 to 2. You can see it here. And then you have the top and the bottom of this, which is, no, that's 0 to 2. Yeah, 0 to 2. And then I think these are also, no, these are 3s. Those are 3s. Yeah, do you see the 9 over here? So these are 3s over here. You see the 9?
Yeah.
You see that your x goes from -3 to 3?
Yeah.
You see the outer integral is x, and you see the limits for that x? So that's -3 right there, and that's +3, and that's a circle. So this y better be a 3 over here because that's a circle, but we also see it right there because it's a circle. It's only a half of the circle because it's only the top half of the circle, and the bottom half of the circle, which I don't have, is not there. Otherwise, you would have a negative square root like this on the bottom. Yes?
So the formula that's in between the dt and the limits, what does that describe?
That could be some kind of distribution of something. Okay. Could be distribution of energy, distribution of temperature, distribution of density, whatever the hell it is. It's some kind of function inside that you're integrating across this object. So that could just show the location of where the object is hotter, where the object is right. Because the temperature is a function of location. Right? As you heat this up, right, put the heat over here, it's going to stay cold over here for a long time. It's going to be very hot. Right? So, you know, the objects do not magically heat right away. So when you're baking something in the oven, what are you doing? Right? You're waiting for the bones to start cooking, and then they cook the meat from the inside out. Right? So you push the temperature probe all the way in, making sure it's 160. Right? Which is
Wait, isn't a microwave inside out and an oven is outside in? Am I not right?
Just happy now. Are we? Yeah.
Ryan says yes.
It's probably the best. Well, we need that.
All right, so I'll by the time you get that going, I will set this up. You all notice the denominator? Denominator changed. It's no longer x squared plus y squared. X squared plus y squared is r squared when we do conversion, because you are not allowed to have any x and y's once you change everything to polar coordinates. So if you pay attention to the formula, which is right there, observe that your f input over there was x, y, z. The output is r cosine, r sine, and z. Right? So those are allowed in cylindrical coordinates. Right? R, theta, and z only. Which is the reason why we had to transform the thing inside. Now, you go in, you integrate, and do we have any advanced techniques for integration that we have to consider?
Inverse tangent something? Derivative of inverse. Would it be inverse tangent or inverse?
There's no z there.
No, the z is going to integrate and just get a 2 over. You're just going to get 2 over 1 plus r squared.
Normal u sub with the other r.
Yes, u sub. It's not inverse tangent.
Yeah, no, so it'd have to be square root.
You see this? You see this r over here? Right? It's a u sub. Denominator equals to u, and then you have already 2 from over there, so that's 2r. So you don't even have to fix the coefficient. This is like the simplest u sub problem that you can get.
You just integrate dz first?
Now, if you go ahead and use inverse tangent, you will be wrong in this question.
It's 1 over square root of both.
Now, you see how the grade dies with that r? If you forget that r in the formula, if you do not memorize the string as dz, r, dr, d theta, you forget that r in there, the killer r, this one. It's not that you are just setting the problem wrong, you will also be integrating wrong, because without that r, this thing over here is inverse tangent. With that r is a basic u sub. All right? So it becomes ln, right, of 1 plus r squared. So there's that. Yes?
You multiply r for the dz.
Yes. dz and r can swap places. The reason that we keep it a unit is because we kept this thing as a unit in our polar. But the answer to your question is yes. They can swap the spots.
So if you were to put the r on top, you make it just 1 plus r.
Do what?
Yeah, if you multiply the r in, why not? It's just, it's a variable. Just that it's r over 1 plus r squared.
You should eat.
R.
Because you're clearly out of energy. What you're saying is no bueno.
Would you integrate the dz first, and then it would just be z, wouldn't it? It would just be z times all that. So you get
Yeah, z from 0 to 2, so z becomes 2.
So it would be 2 over 1 plus r squared, and then you distribute the r.
Mm-hmm.
So 2r. It would be 2r over all that.
Mm-hmm.
And then you integrate the second row. Oh, wait, and then you can.
You know, so you have to put like 1 half on the outside.
Why'd you put 2r?
I don't understand why.
The 2 is when I integrate z.
Oh.
That 2 is when I integrate z.
Oh, because it's just a constant. So on your side being. I feel that.
Uh-huh. So that's that. And then you use your u sub. This becomes 1 over u. Integral of that is ln. So we have 0 to pi ln of 1 plus r squared from 0 to 3 d theta. So that's ln 10 pi. It should be good.
Yeah.
All right. Let's open the gates of hell. So, spherical coordinates.
0.
Now, these coordinates are a little bit tougher to understand because these coordinates have two angles. There is angle theta, and then there is angle phi. And you have to work with both of those to work, to be successful with spherical coordinates. So first of all, behold a sphere. And we're going to realize that there is this path from the x to y, and that is operated by angle theta. At the same time, in the sphere, so the radius r that first goes along x-axis, you swing that along y, and then you can also, from z-axis, swing this way, phi. Now, it looks weird, but you've seen something like this before when you dealt with bearings. Hold on. When you go back to your trig, you learn that when you have your xy coordinate system, the angles are measured from x-axis towards y-axis, angles theta, that's the positive direction, or going this way for negative theta. This is what you learned in your pre-calc class. How to measure angles. Now, at the end of your pre-calculus class, you learned the coordinate system, which is actually north, south, east, and west. And then you measured angles from the north or from the south. And that is what we are going to use now for the measurement for phi. So now I'm going to call that angle phi. So the angle that will be measured from x-axis in the xy plane of the ball, it's going to be theta angle, and that's polar coordinates, all right? You stretch out the radius. So, guys, the xy plane is here. So this is the origin, and I go and I stretch out, let's say, a 2, right, units radius. Now, this one is going to be, let's say, x-axis, and then I can rotate around, right, in the xy plane, and what I have there is the polar coordinates, which is 2D. But then, That's the flat plane that we created, right, which sits on the xy plane. Now, what I'm going to do is I'm going to add to that plane a z-axis that goes up and down. Now, for the z-axis, the measurement goes this way. So positive z-axis is where it's a 0 angle, and then as it goes down, you measure positive phi. It goes the other way, measure negative phi. So how do I create a ball? Yes?
What other axis is it like respective to? So like it could rotate.
It doesn't matter.
Okay.
That's the key. I have to explain that. So now look. When I create my circle using polar coordinates, which is draw out R and the 2 pi around, right? That creates a circle. Once I have that circle, what I'm going to do now is I'm going to flip that circle pi. You see that this half swipes this part, this half swipes the bottom part, and it creates the ball. See that? So what I do is I go radius, I go 2 pi on theta, and then I go pi, because I just flip it. I go pi, like a pancake. Plop. Now, see, it doesn't matter if I flip it around x, I create the ball, or if I flip it around y, I create the ball. It doesn't matter. What's important is that I am flipping it only pi, not 2 pi. So to create the ball, what we do is we have limits. Well, we'll see the way it goes. So now let's. Now I hope you understand the way these coordinates work. They're really strange, and I'll give you that. So the coordinates now are rho for the radius, phi, and theta. That's spherical. That's the spherical coordinates. And as you can see, you have 2 angles. So this one is measured off of z, and this one is measured off of the x. Now, rho and theta together are creating the polar, good old polar plane, which is in the bottom of this. So clearly, if you see something with sharp edges and you try to use this, I will know that you have no clue what you're doing, right? Because both spherical and cylindrical coordinates are looking for round shapes, circles, flowers, cardoids, all of the things that we did that have just circles, right? If there is a rectangle somewhere, well, go back to your x, y, z, because that's what the coordinates are for. What happened? Rho, yeah, it's a radius. No, it can change. Because depending on what you do with it, right, it's not going to draw out the ball. It might do some kind of spirally thing, or, you know. You could fix it, yeah. It will be a very strange one, but yeah. I mean, if any one of you are good with 3D graphics, obviously you're going home and programming this thing to see what it looks like. Obviously. No takers? All right.
I'll just download Fusion 360 real quick. She knows. She got it. She got my joke.
Now, what is the integral that we have in spherical coordinates? This is the one that you are remembering, and you will use it to set up problems. So the triple integral is, so f of rho phi theta. All right, so now rho squared sine phi d rho d phi d theta. D rho d phi d theta. And now we need the limits.
Yeah, my Greek letter game is weak.
Oh, you don't know Greek?
Yeah.
So wait, I have a question. The circle with the line going straight up, is that omega?
That's phi.
Well, no, not that one.
Omega is this. This is rho.
Like, like
Omega.
Like at the beginning for
Like
circle.
PHI?
Yeah, circle.
Omega is what happened?
What's this?
Oh, beta. Well, let me write it. So alpha and beta on the outside.
The Greek alphabet. How about that?
Yeah, for real.
Do the whole thing.
AB, G of phi theta, and H of phi theta. There we go.
Phi is the one that like extends and has, right?
What happened?
Rho. Sometimes I just write rho and phi and they look the same.
Difference between rho and phi? Rho, phi.
Okay.
Better.
Is alpha the first letter in the Greek alphabet then? Yeah.
Alpha and omega, beginning and the end. Omega is last.
Do you know them all in uppercase?
Yeah.
Can you show?
Can you just write the whole alphabet on the board?
Google it, I mean.
Google it, I mean.
Have you?
Mm-hmm.
I want to Google that actually. Uh-oh. I just took out an apple though. It's right in front of me.
The first order of business is someone at some point in life told you that the volume for the sphere is 4 pi over 3 r cubed.
Yeah.
Prove it. Prove it. Yeah.
And R is the same as rho, right?
Well, radius will be r.
Why do I need the sphere?
You need the sphere?
What?
He needs a sphere.
Like a physical sphere to hold?
What?
Wow. I don't understand. Are we all really looking for spheres right now?
I don't know why. I explained everything. You know the limits. No.
Yeah. I've managed to like throw
Yeah, phi is like it's a little more
I was still a kid once. I begged them to not make me, and then it almost died. They made me go lay him during like our rope obstacle course thing, and then like somehow like the rope escaped my hands and went around the
Z X I Psi?
Sorry.
What is it?
Wait, which one's
C.
That's the weirdest looking symbol I've ever seen in my life.
Wait, which
What was like this?
It's like a backwards E that looks like sharp.
A backwards that looks like what?
Look at
Read
that.
a little thing on the bottom.
There's the capital one has like it's like 2 brackets and then there's like a little bow tie in the middle.
What? What's happening?
I don't even know how to pronounce this
All
letter.
right, how's it going, guys?
It says the pronunciation is XI.
C.
Psi?
No, we already have a psi though.
All right.
Yeah, we
So-
do, actually. Yeah, psi is like the trident.
What do we have? It looks like this.
Yeah.
So what
do
about the other one he's talking about with bow tie? What
Yeah.
does that look like? What is he talking about?
Not even, it's like a bow tie. Or just draw something with a bow tie.
So let's set up.
Basically draw a bow tie with
Guys.
a bracket on the top and bottom.
We are looking for the volume, so we don't need this.
Like up and down.
Now, you have to memorize
What do we have to memorize?
this.
Oh no.
That's the string for spherical. That's what you're learning in a class. So you have to memorize the string for cylindrical and spherical integrals. All right, so since I'm not using the integral, since I'm calculating the volume, I'm only going to put the string here. Sine phi, d rho, d phi, d theta. And now, remember what I said. The outer angle is the one that swipes the radius around, so that's 0 to 2 pi. The z one goes from 0 to pi, and the radius goes from 0 to r. That's the d phi. D rho. So you should be able to. So go on. You better get 4/3, otherwise.
You just did that all in your head just now? Or do you have the answer?
Yeah, we're looking for this.
Oh, jeez, right there.
That's just like our regular volume.
It is. Maybe that's what this problem is figuring out. It's like
Yeah.
0 to pi. So radius. 0 to 2 pi.
I don't know. I don't know.
With the points. So
lots of Greek letters. It's kind of scary.
My rho and my whatever the volume
Phi.
Phi?
Yeah.
Is this phi?
Phi.
Except
This phi looks like a backwards alpha.
except lowercase, right? And the uppercase is tried looking one.
Is your 5?
Uppercase.
Can you distribute a
Is it
5?
uppercase is like some fancy.
That's rho.
Oh, uppercase is like
That's rho.
like a circle.
I thought rho was
Like the letter I.
Yeah,
Like the letter I with a circle. Letter I with a circle.
Oh god.
Oh, phi. Oh, yeah. Uppercase phi is like a sideways theta. It's like the circle with a line down the middle. Not like going up and down. That's the uppercase phi.
Then what's the one that looks like a trident?
The trident is psi.
So-
Yeah.
I'm so mad.
I wonder what your Serbian authors are going to think. This, the munching sounds in the background.
I don't care.
That'd be so funny. I wish I just would have just randomly discovered your channel and just been like, huh, I could just learn calculus from this guy. Like, for real. You can literally just get a free education from the whole channel.
There's thousands of them.
Like,
Yeah, but then they make you show a degree.
true.
You're not really even paying for it.
Well, say you want to make your own business, though. You could just, learn calculus and then make your own business. You don't need, and you'll be the CEO. You don't need a degree to start your own business.
Exactly.
You do. That's what I want to do. Hashtag goals. You're gonna drink that?
What?
Yeah, of course.
You can have some of mine. Drink that.
I thought it was so serious for a second.
Yeah.
I didn't know.
You want some of my water?
I'm just looking for a facial expression. That's all.
Oh, wow.
You want some of mine?
Please don't throw it.
Okay. The first integral we have to do is the d rho, which means that this is a constant because it has no rho in it. So we are starting with rho cubed over 3 sine phi, computed from 0 to r. And when you plug in your r and 0, all you get is r cubed over 3 sine phi. And you know what? I like it because I already have r cubed. I already have over 3, right? So if you look at the formula, I have these two components already. Nice. Moving on. The next integral I have to do is this guy. That's a constant because it doesn't have any phi in it. So the outer integral 0 to 2 pi remains. R cubed over 3 is a constant, leave it alone. The integral of sine phi is negative cosine phi. Yeah, go ahead and fix that. There we go. See all the erasing now? Yes, the integral of sine is negative cosine. Going from 0 to pi, we still have d theta. Now,
It's still R3 over 3 because when you plugged in R, it's still R, right?
yes, we are plugging in 0 and pi for phi.
But I mean when you had the double integral, since you were plugging in R, the R just stays basically, right?
Yeah.
Okay.
So now we have negative cosine phi plus cosine of 0 d theta. Cosine of pi, I said. So negative cosine of pi is negative 1 and the negative 1. So this thingy over here is 1 and this thingy over here is 1. So we have 2. 0 to 2 pi, 2r cubed over 3 d theta, which is 2r cubed over 3 theta from 0 to 2 pi. When you plug in 2 pi, 2 times 2 is 4, and there it is, 4 pi over 3 r cubed. Of course, it's math. So now, thank you for the setup. We want to calculate some nicer objects. Here is the perfect definition. If you take a look at the, right, this is a cone. Now this cone is not flat on top. This cone is actually having a rounded part of a sphere, because you see that that cone was cut out of the sphere. So there is a curvature on top. You can't compute that with the regular x, y, z integrals. Not just because it's round in its, right, you could probably deal with that and suffer through all of the trig. So the issue is that this cap over here, right? How do you deal with that? And you would have to actually set up multiple integrals for that as well. So this would be a problem that would be a living nightmare to do in x, y, right, rectangular coordinates. What you can do, however, is you can set up cylindrical integral. You see, spherical integral. This part is part of a sphere. And if it's part of the sphere, spherical coordinates should do the trick. You know that your radius rho is 4. That's given. And you know that the angle over here is pi over 6. Well, that's your phi. It goes from 0 to pi over 6. So what do I have? I have the 4. That's this, on the x-axis. Right, from the origin, I have 4. Now, I have the full rotation, right? You see the green arrow on the bottom? I have the full rotation around for my theta. So I have 0 to 4 on a rho, which is a radius. Then I have 0 to 2 pi for the full circle, because right, you can cut it in half, you can cut it in quarter, you can cut the wedge out of this. And then you have to change the theta. So theta is 0 to 2 pi because it's the entire thing. And then you also have pi over 6. So how does this work? Look, radius, lift it up, that's the second one, to put pi over 6, and then rotate. And you see that it creates the same shape. So radius in x-axis, go up pi over 6 from z, and then rotate 2 pi. Creates that kind of shape. You can do it, right? We have that mobility to do that. So that's what I used to do when I was taking the Calc3, right? You do the hand gestures, right? Just the same thing when you go, right? You take physics And then you have the, you know, the right-hand rule, the left-hand rule, right? That's the...
Use both at once.
Exactly.
Yeah.
Right?
Right-hand rule.
Yeah.
The direction of the.
Use it for torque and
Yeah.
Yes.
electromagnetic. All this stuff.
The president, right-hand rule. Right?
Yeah, I was just doing.
Right?
Right-hand rule.
Right-hand rule. All right. You're not pleased, I can say. Or you're spaced out. You're spaced out. You go. You can. No?
Oh.
No, she's in a rush. I know. Wait, what happened? Got canceled?
No, it's actually.
Oh.
Oh, that's right.
I heard it was very good.
So,
I've been waiting for this for like 2 years.
what would be the setup
Calculate the volume.
for something like this, right?
Volume of the cone and the volume of the dome on the cone and out.
Yeah.
You can't see your,
So we have 0 to 4
you can't see your,
for row. Thank you. So we have 0 to 4 for row. We have pi over 6 on phi. And I have 2 pi on theta. So the volume for this cutout will be rho squared sine phi d rho d phi d theta. Theta is 0 to 2 pi. Phi is 0 to pi over 6. And this is 0 to 4. Forget about it doing this in the XY coordinate system. It's a living nightmare.
Like, could it be done?
No. And then you just integrate. Now, as I said before, right, the first integral is just focusing on rho. So you don't have to worry about sine theta gets, right, so that's going to be, what is that? That's a 4 squared into, that's 64 pi over 3, the cosine pi over 6 root 3, 2 minus root 3. Done.
That's the whole thing.
Yeah, that's the answer. Easy.
Easy. This is all
It's 3 consecutive integrations. It's not a problem. They'll cut one. That's okay. That's what paper is for.
Wait, isn't that the same thing we just did? Isn't it?
All right, now.
Just at different limits.
Yes.
yeah.
Oh, okay.
It's the same equation. Is it the same equation for every shape?
No.
So
Look what I'm writing now.
Okay.
Plane in spherical coordinates. Now, guys, if you have a plane in spherical coordinates, the equation for that plane will be given as rho equals a secant phi.
Oh God.
Yes?
Thanks. Please. You know what? I'm just gonna never speak again in this.
So now, if I have a plane, oops,
Just like secant and like ultra. Yeah.
so if I have some kind of plane that goes to, let's say, 3,
All three.
that it's, plane, you know what, XY plane, that has to be parallel to the floor, right? XY plane. So you have something that is parallel to the floor. So this plane over here will be given as rho equals 3 secant phi.
You're rolling your fire.
This has a little curly at the end.
So
Phi.
Rho
Phi.
equals a
Rho
secant phi.
A.
Just remember the little curly bottom.
Am I reading rho equals a secant phi or is it opposite?
Yes, A secant phi. Phi.
PHI.
R upside down.
Not FY. PHI.
So now the same problem that we had earlier, except now it has a flat top. If the top is flat, right, our integral is going to be, and let's say that that flat top is at 4. We have integrals, and then again, I'm not going to use the function, so I have rho squared sine phi d rho d phi d theta 0 to pi 0 to pi over 6 and then 0 to 4 secant phi. So you see that now that I have the flat plane on top, it's the same problem like before. So we had that pi over 6 established.
So we do always.
You see that pi over 6 given? Yeah. So it's the same problem except now it's not a cutout of a sphere. It's flat, like the cone for ice cream. So this calculates the volume of the ice cream cone. Yes.
So we always use the same equation. It's
Yes.
Wouldn't it be better to use cylindrical?
Yes. But
oh.
why simple if we can complicate things? Yes.
So we always use the rho squared sine phi.
Yes, that's a string.
And then so always for every shape, and then it just matters what we input.
Yeah.
And the limits. Yes. So guys,
So
the
rho for
limits
plane-
define your shape. Yes.
So then rho for plane is this, but it is different for a
Slanted plane is different. Yes.
You watering it?
We'll keep it simple and then.
It's growing, so you're watering it.
what?
You're watering it.
Not pouring water on my head.
You got my joke. You got my joke.
I learned not to get involved.
I got the joke.
Oh.
Like garden.
It's like a plant.
Plant.
He's calling me.
Now, you're going to love this.
Well, you said this is the top of the bell, right?
Yeah.
Where is the fire outlet?
First, like you said, it was 0 and 4, then you swap it 4.
Okay, let me.
Oh, no, thank you. That's a good definite pause there. I'm okay.
So, the next object is this, but first let's, guys, focus. You are looking at, I need this can now. Look at the can.
Yes, the bottom has a little indentation.
Do you see?
It's a little dome.
Look at the can.
Okay.
You want one that's
It's a little
sealed?
dome on it.
You see it has a little dome on the bottom?
Yeah.
That's what you're looking at, except this can, oh, you have the, well,
Yeah,
no, this
I have
one
one
was,
that's not open, huh?
no, I was right where I wanted to be. So, right, there is a sphere poking into the shape. But let's go. First, you had the question. What was the question again? The difference?
The difference between the first one, we just said it was the row was between 0 and 4.
You see, the shape on top
Yeah.
is rounded, and over here, the shape is flat.
Yeah.
So when you have a flat plane, this is why I wrote this thing in red over here saying xy plane, right? Xy plane, which is z equals planes, are a sine phi. So you know that. All right, now we are going to combine the two worlds. What you have over here is we have pi over 4 angle. We have flat plane at 4. They have it at 2 actually. And then you have over here 1.
Just calculate the area of the top and the bottom part for the volume.
We are calculating the volume, yes.
But not of the entire thing.
Of the entire thing. It's how much can you fit inside this shape. So that's what we're having.
So it just matters what shape the top is.
Yes.
And the rest of it. Yeah,
It's just a cone with off.
But no, that's scooped out. The sphere is scooped out on the bottom. The can.
Alright, yeah.
Look at the bottom of the can. See that?
I got it now.
See the bottom of the can?
Yeah.
All right. Now this can is gonna go places. All right. Got it? What?
better. She said like a bite out of the bottom of it. Why you do that? I don't know.
No, you take an ice cream.
I don't think you can actually bite into this because it's.
Ice cream scoop at the bottom.
Yeah, I know. The can is traveling now through the class, making sure that you all see the scooped sphere out of the bottom. So this is the bottom of the shape, right? And oh, it's a business call, right? So there you go. You have the sphere that it's scooped out, right? So that's the bottom. Now, we have the standard string, rho squared, sine phi, d rho, d phi, d theta. Theta is the first one that it's easy to see. Is it round all the way? Right? All the way? It is. 0 to 2 pi.
So is that always the equation for a cone, basically?
Now, we have the angle at pi over 4, so 0 to pi over 4.
So if we want to take the integral of like a cone with like a slice cut out of it, then that would be like the only thing you could change. Would be the
Yeah, you just change the limits. And then we have the rho.
Why is it 0 to pi over 4? That's the thing.
That's this one.
Oh,
It's like that's the equation of
the truck.
Yes, for the.
Yeah, when you revolve
That's how much.
auto.
Right? That's that on both sides.
I understood that.
Whatever it takes. And then we have the rho. It's scooped out 1 on the bottom, which is a sphere, and on top is 4 secant phi, because it's 2 secant phi. It's a plane. It's a flat plane on top.
Oh, I got it.
So we should definitely know the integral of
Because secant is 1 over cosine, and you have a sine. Sine over cosine is tangent. So use sine.
Okay, that's not so bad then.
So you do it from like the top of the arch, like the very top.
What do you mean top of the arch?
Like it's the spherical like cut out at the bottom. You do it from like the absolute top of that to like the top.
Yes, you are. Again, you have your R is going from some center somewhere up to here, up to there. So that's the lower limit, upper limit for rho.
I guess I'm just a little confused.
And then
as to
Z,
how you-
which is d phi, 0 to pi over 4. And then you have all around 2 pi.
I guess I'm just confused as to how then you would count for like the little angular parts on the side.
Which angular part?
Like the area around the sphere. Like I don't understand how you're accounting for those parts.
But I don't have any area, any other parts This is it. It's bounded from all sides. The roundness like this is pi over 4.
Oh,
The
never
top
mind, never mind,
is
I
the
get it.
secant.
Okay.
The scoop on the bottom is 1.
I get it. Never mind.
And it's the full rotation around for 2 pi.
For a
Got it.
it's always going to be the z value secant phi. Like for that upper bound on the like for a
Yeah, whatever the yes,
z
or
value
whatever.
secant phi.
Yes, whatever z. Yes.
Okay.
I call it a secant phi. Yes. So, and now you go and you integrate. You get rho cubed over 3 again, and then your rho, it's rho cubed, so that's going to be secant cubed, so 8 secant cubed over 3, and then that secant cubed is going to be interesting to deal with as you move on, because it becomes a cosine cube. Then you have fun with that, right?
Lots of calculator.
All right. Should we integrate this one for fun, or move on to the next?
Wait, no, we already did it. No, let's go to the next one. We've already done this.
All right. Well, now I have interesting questions for you, because something very similar will be on a test that you don't have.
This question?
Next one. Good effort.
Is the final similar to the test that you change? You don't just like wildly change the format.
Do you want me to?
No. I'm trying to decide what answer will best suit you. I feel like if I say no.
Wait, but if we're taking the final on the last day, does that mean we're going to get like our grade back?
Next week at some point. All right, so...
No, but I mean, like we can come to the school and get it from your office?
No, it's the final. Final stays in our... We'll deal with that later. All right, guys. Let's actually do 2 problems because we have time. 40.
We have time if I don't ask a lot of
Should I?
questions.
Is this enough paper or should I just put my paper?
Flip.
Okay. She didn't even see it, but you're right. This would be on
It will be on the
Yeah, would this be one that you might use like on a test per se?
You said, yeah.
test.
All right.
Might use. Do they work?
Oh,
Wait, what?
Good luck.
What's a unit ball?
the ball is like the unit, like the one.
Unit ball? What's a unit circle?
The one, but like rotated.
What's a unit circle?
I get it.
It's
I
a
get
circle
what
with
you're
units
going
on it.
at. Yeah.
Except
With the
you add
radius
the
equal to
phi.
1.
It's a sphere with radius 1. Good. All right,
And
go.
it just goes. Okay.
Set this up.
You're
Unit
sure it has a
ball?
hole in it?
The unit, set up the unit circle.
So it has a radius. It's a sphere with radius 1. D. What? Are you wearing pole? Yes. Okay.
We had a whole discussion about what it was.
Incredible.
I know. Like,
I'm hilarious.
This is part of my graph.
What is this of the unit circle?
collection.
Do what?
why are you putting your shirt?
That's holes.
You need to integrate this.
Oh, okay.
Yeah.
And actually buy them.
But
I was just like, I was planning on going to like do like work on my before class today, so I wore like crappy clothes. But then he canceled on me. Yeah.
Oh my god. How do you do this?
The DV is just the same.
Chain rule, easy.
Well, no,
Oh wait, no, integral chain rule.
X
Never
squared
mind.
plus y
I'm
squared
stupid.
equals R.
That was the dumbest thing I could have said.
I
Actually, I would
think
have
I
said dumb.
beat you today in terms of dumbest things said.
Wait, so it's a sphere with a radius 1, right?
Life is meaningless.
So it's 0 to 2 pi, 0 to 2 pi again, right? No. The first integral will be from 0
Then
to
you have to
pi.
like work with
The
noise.
second one will be also 0 to pi.
Like
Wasn't it just the x
people
equals
are
the
annoying.
theta? D phi, d
0 to pi, 0 pi, 0.
Oh. What did we say?
I'm so confused.
Gosh, Shilvana.
I'm struggling.
I definitely am. I think it's resolved.
Yeah, I had got that. I got it.
I'm staring at That's my philosophy.
Alright.
And then so much intensity.
And then you go 0. And then you take off.
What? Are you drawing the unit ball?
Yeah.
Okay.
Alright. So we have here and here. Would this be 0 to pi?
Well, we know that the ball is the regular setup.
Theta? Theta is 0 to 2 pi.
Theta is 0 to 2 pi.
Because the other one is 0 to 2 pi.
Well, yeah.
Phi 0 to pi.
What's our first? What's our
And
first
radius
bound?
is?
First integral? What's our
Radius is
bound?
1.
Radius 1. Good.
First from 0 to 1 is
Yes.
the first bound.
All right. So let's talk about this. No. 0
No?
to 2 pi.
0 to 2
Are
pi?
you doing the inside or the outside?
This is the outside one.
Outside
Let me
2
draw
pi.
them all. How about that?
Outside 0 to 2 pi, and then you have,
I missed the square over here.
and then you
Isn't
have
that
0
like technically the
pi,
x's?
and then you have 0 to pi, and then you have 0 to 1. He nodded at me. I don't know if that means it's right, but
How is this
It's
one
not
0
again.
to pi and this one 0 to 2 pi?
It's right.
because phi, because he's moving. I'm not going to use this plate because it's direct, but like you like only have to turn it once.
Halfway.
You
You only, yes, you only turn it halfway. All right, let's take a look at this problem together. It's a lot of heated discussion about this problem. I know it's very interesting, but let's actually solve it.
One half and the top is the other.
All right.
Like that thing you did before. Right?
Yeah, that's the whole point of what.
One more piece of information is that equation of the sphere is x squared plus y squared plus z squared equals to rho squared. You know this from chapter 12? I think 12.1 was, or maybe even earlier.
Oh, I get it.
It makes sense.
Now,
I don't know.
from there, rho is equal to square root of this, which actually compresses our problem to negative rho cubed. Because the half is the half for the square root, and you have the whole thing x squared, y squared, z squared, that's all rho. So we have that set up. Now, we know that the dv has the string of rho squared sine phi d rho d phi d theta. So this is this. That is what you're memorizing. Now I have the bounds for the unit ball. Unit ball has a unit radius, which means rho is from 0 to 1 because it's a unit. We also have theta that goes all the way around from 0 to 2 pi on the outer integral, and then 0 to pi for the inner. And the entire problem is solved. This is over here set up for beautiful and wonderful u sub, exactly. And sine phi is just a constant in terms of rho, so you copy that, and you go computing, so it should not take long time for you to compute this integral. However, the important part for this problem is to realize that x squared plus y squared plus z squared, and then square root of that is rho, because of what rho is as a sphere. You know that for the circle, right, for the circle, you had the square root of 9 minus x squared. We had that earlier, right? So, square root is there. The string, you must memorize and know. And then the setup for the ball, guys, for any sphere, which is just a ball, like a basketball, or tennis ball, or whatever, they all have the same setup, except this number is different, which is the radius. So how big is it, right? Is it a ping pong, right, ball, or a basketball, right? That's the only thing that changes. The rest is the same. So if your region D is a ball, then boom, that's the block with whatever the radius is, whatever the function is, converted into rows and things, and then the string which you are memorizing. So I have one more problem.
When we talk about spheres versus balls, just to have a little...
Sphere and a ball, same thing.
Okay, because it sort of made it sound like the ball was region inside the sphere, and the sphere was...
Yeah, same.
So if we like call them the same thing.
It will be weird. Your basket sphere. It makes no, yeah, it's basketball. Baseball, base sphere. It's weird, right? Yes. What's funny? What's funny?
Because I didn't have $1 on me, but I had like... Well, actually, I had $2, and I spent it on the vending machine because I was really hungry. So I had 75 cents.
I don't understand what's happening on that side.
I don't know, that side of the room. We'll just ignore them. All right. It's right there. All right, guys. Now, here's the challenge for the day. If you manage to do this one, you have mastered the art of...
Damn it.
No, of spherical coordinates. That's it. Tomorrow is going to be interesting, for the lack of the better word.
What is tomorrow?
Tomorrow is Wednesday.
I thought today was supposed to make you.
Well, it is already. All right, so D is the solid between spheres. Rho equals 1, rho equals 2. Centered at the origin.
The object is centered at the origins, but those two spheres have... Is rho radius? The spheres are centered or the object is centered?
So are the spheres intersecting? I'm confused.
Okay.
What are you describing?
There you go. Say it.
Hollow sphere, so you take the interval and small.
Yes.
Oh.
So, all right. What I need you now to picture in your head, and you should have this as a concept. Do you guys know that there is air in the basketball?
Yeah.
Great. Now, exactly. Now, what you have is you have the material, right, which is containing that air. That material has thickness. Now, imagine if that material was thick like that. So you're going to have that everywhere, right? So it's a very, very, you know how eggshell is very, very thin?
Oh, it's
Just make the eggshell be like that thick. All right. So make the material out of which the basketball is made this thick. So you have the outer sphere, which is 2, and the inner sphere, which is 1. The material is in between those two spheres. So it's a big sphere, scooped out the sphere in the middle. So it's just hollow inside. But you look from any side, you don't see any holes in it, right? You look at the ball from any side, you don't see any holes in it, but the core is missing, right? The core of the...
You ever see those videos where people like...
Except make it into a ball and then yes. All right,
And
good.
without-
hollow
And
out
then put it back
watermelons.
together.
You ever see those videos of people like hollow out watermelons and then they like put them back together, and, or they just have like one giant watermelon?
What are we saying?
You ever seen those videos?
I've seen a video of a person eating a watermelon.
Have you ever seen ducks eating a watermelon?
No.
It works.
Oh yeah, there it is.
What's square?
It's like,
Keep working. I like this guy.
yeah, exactly. Yeah, this is what I was talking
Yeah.
about.
Oh,
They,
You
like,
know this.
They skin. It's like a skinned watermelon. It's like a skin.
He has to speed that up. That's sped up, right?
It's like a.
No, that's actually.
He does not do that.
He's just drinking.
let's not. Thank you.
Alright. What?
That was fun.
It's like Joey eating chicken and Joey.
Yes. Alright, so how far are you with the problem? Are you done?
No.
We're not leaving until you're done with the problem. And I have all night, so.
Alright, so hi. What do you want to do? Play some poker?
Alright, Jane,
What's that?
Oh, frisbee.
You'll pass.
That flies nice.
That's very nice. Like slow motion.
It's gonna fall apart.
I know.
Try it anyway.
It's yeah.
No, that's when
If it goes fast enough, they'll stay together. But
There it goes.
well,
You missed both of them.
you
There
try.
it goes. There it
Good
goes.
effort. What is happening? This is a fever dream. You know what's happening. Plates are flying.
I was trying to do a problem.
That was happening.
Alright, so
Wait, are we calculating the area between the two spheres then?
no, you're calculating the integral. And the integral is happening.
No, I mean the
The
volume between the two spheres.
No, you're not calculating volume because you have this. If this was just that dV, then it would be a trivial problem because you have a big sphere, radius 2. You can compute that with a 4 pi thirds r, right, cubed, and then you subtract 1 from there, right?
Putting this on road.
Yeah. You just subtract the two volumes.
it's landing right where the water
So
is.
two well, like, or like, yeah.
Well, if you're looking for the volume, why would you do the integral?
Oh.
Yeah, if you can do the formula and subtract, right?
Yeah.
But this one is not looking for volume because you have something that you're integrating, right? So this is a 4D question. It's a 4D question.
Oh no. I can't visualize it.
My brain is hurting a little bit. I was trying to visualize. I think you need to do this one in as if
I will see you guys tomorrow. I'll have a few questions.
Enjoy the movie.
I hope it's good.
Is this a ticket you need?
No, it's fine. Okay. Thanks, though. That's
That's right.
I gotta do this one. I gotta do this one. Why is it so
Did you not tell us that? Because you said that's what's good. So that's for. Oh, I didn't see it. Oh, I've done that.
solid or just?
No, just okay. I don't know. Which one? I cannot explain. Like,
I think it's On the upside, it's, I mean, it's 0 to pi, and then it's 0 pi, and then 0 to 2, and then you do that, and then you subtract.
Yeah, you calculate one sphere and then the other, and then subtract one.
But we're not trying to find volume.
I just put the last. What are we trying to find?
I know, he said it's a 4D.
What?
He said it's a 4D. I don't know.
Yeah, because we have 3D over another.
But I don't really know what.
Well, no, but you could just take the DV out and be one of them.
We can't just.
Oh, for the moment I freaked out that she ran out to see the movie.
And then it would just be that
her.
function raised to the negative 3 times.
Wait,
Times
this is something that
Yeah, well, so there's a row and zero minus L. So there's a row, right? I'm going to change the x squared plus y squared plus z squared down.
June 2nd.
Oh yeah, you could change it to row. Yes, so you're right. dv over row to the third.
Yeah.
Right?
Why is he still carrying around a ticket from
Or you could just say row to the negative.
Emotional.
It's 219.
No, just row to the negative 3. It's negative. So just confused.
I'm a little confused as to what exactly we're doing.
Oh, true.
We're just solving the integral. So now let's do it. All right, here we go.
The road disappears.
You can put, if that's confusing, you can put this. It's the same thing. But keep it there, doesn't matter. What do I have? I have 1 over rho cubed. We know that x squared plus y squared plus z squared and square root of that is rho. And then there is 3 over there, so rho cubed. Then we have a string of rho squared sine phi d rho d phi d theta. And this is 2 spheres, one inside of the other. So 0 to 2 pi for a sphere, 0 to pi for a sphere, and then 1 to 2 on the radius. And now you just simplify.
Can you try to draw this?
No, because you can't see it. All you would see is this. You don't see anything else because it's a full object, and only the middle is missing. The middle is out, and then this distribution function, whatever it is happening in the meat of the. Right, like you said avocado, because avocado has a perfect round middle, right? And imagine that outside of the avocado was also perfect sphere.
And the 1 to 2.
You take that middle out, you put the thing together, so whatever the avocado is, the thing that you actually eat, that's where all of this distribution function is happening.
Oh, okay.
It's like the thickness of the whole sphere. But from 1 to 2.
Yeah, this is a very, yes. You know how eggshell is a very, very thin?
Yeah.
Well, this is actually very thick, right? So you have inch from origin to, you have 1 inch from origin to 1 inch, right? And then 1 inch to 2 inch. That 1 inch to 2 inch, that's all material all around spherically. And the size inside, right, is...
it could be an eggshell if it was 1 to 2 millimeters.
No, because egg is so big.
It would be like 1 to 1 point.
You would have to have the eggshell to be very, very small.
Because then it's the thing is it's the ratio of the object. The one radius is 1
Yeah, the
and
1
the
to
other
2.
one
Yeah,
is
no, it's
2.
the thickness of the sheet. Yeah, no,
So it's like the inside would be too small for 2.
So now you have your ln, right? So it's going to be ln2, and then you have your sine, it goes into negative cosine, and that gives you a 2 from there, and so on. So you can, I mean, if you do enough of these, you can do it mentally, because they always go in layers. Another one? Okay, why not? Sure. Okay, fine.
This is a unanimous agreement throughout the whole class.
He doesn't need our
I don't.
He said multiple times.
This is a dictator.
Yeah. So,
Yes, Jake.
I don't know why I
class.
bothered.
What? I do speak for the whole class. Am I right, guys?
Would it make you
That was a
happy?
yes. See? There
Would
you
it
go.
make you
That's
happy?
what helps you sleep at night.
Would it make you happy if we say you do?
A little bit, yeah.
Okay, then yeah.
Thank you. I am now happy. I was sad before. Now I'm happy.
Depression?
Who needs pills? Who needs drugs? Actually, be drunk on that.
All right.
Okay.
There it is. Grand finale for today.
Bowl.
You have
This is ugly.
all my drawing skills are.
No, I just need.
Oh.
Listen.
That was so cute. That was so bad. That was lovely.
With 5, you can do it's only half. Like, is 5 then from 0 to pi over 2?
It's fine. From 0 to pi over 2.
I don't know. Because if 5 were 1, then it would be a full sphere,
I
right?
think you're messing up. Either, okay, I won't probably not explain that concept. I said it's 0 to 2 pi, and then 0 to pi, and then square root of 4 plus r squared to square root of 29. That's what I. Yeah.
No,
But
I'm
no, I
that's
zero
right. I think.
0 to pi over 2 though?
Because it's not full circle.
First balance.
0 to pi.
What's the min? So it's from the minimum. What's that number? Is that square root of 29?
I thought it was 24. Yeah, it's 24.
Is that square root of 29?
Wait, no, wouldn't it be just
or
from 0?
Professor?
Yes.
Is that square root of 24 or 29?
29.
Then why pi over 2 then? Wouldn't it be 0 to pi?
Maybe it is. I think
It's 0 to pi and also 0 to pi for the second one, and then the square root is all that.
because it's a full circle, so it's
I don't know
0
if
to
it's
2
right.
pi.
No, it's a half circle. Well, it's a full circle. Oh, no, you're right.
It's a circle, and then
Theta's going around, right?
yes.
So theta's
It's a
from
half
0 to 2 pi,
sphere,
because that way is a
Yeah.
full circle.
But then
Okay.
if we say it's from 0 to pi, that would mean it's from 0 to pi. For pi, that would mean it's a sphere.
Yeah, so what if we go from
0 to pi over 2?
pi over 2, so we start in the middle and then we go all the way. So it's like the bottom half. Right? That's the bottom half, so we start at pi over 2 and we go to
Isn't that the same thing?
pi. Well, I mean,
0 to pi over 2 and pi over 2 pi is the same.
yeah.
But then that doesn't make sense.
I think you're right. I thought we might have a.
Where are you using phi in your back? Where do you get that?
Well, don't look at that.
Using phi in
We
your
have
back?
find the balance,
What?
but not pi.
Wait, what?
Yes, there is.
What'd you say?
Okay, I'm writing two different things.
Listen.
0 to 2 pi,
Yes.
0 to pi,
Square root
and then square root of 4 plus r squared
because it's half a circle.
to square root of 29.
But so here's my problem
Right.
with the last bit of it is, do we care where the circle is located? Like,
Volume? No. I I mean, for volume, it doesn't matter as long as it's consistent.
Right.
Like the volume would be the same if it were at that speed as opposed to moving it up like
Yeah.
five.
So yeah,
If you're not down, why not?
So
Oh, yeah, you do nothing. Is that what you have to go?
Always assume.
We are playing basketball, right? We are just playing basketball, What would be the equation that we're it's gonna be wait, I actually might have got this. What's the equation we're integrating? I don't think it's just the same one.
You're just looking for the volume, so you are not integrating equation because it's already 3D.
What?
Can I show you the thing and then ask if it makes sense?
Yes.
I'm gonna slide over one. Because the radius is the same. Okay. We're just gonna integrate where's
Yes.
So then we can move this up and down. Can we just take this equation and try and get it from
oh, hey.
yes. Like square both sides.
I tried that, but then it gets you x squared plus y squared minus c squared. I tried that, and then it doesn't.
Okay, let's take a look at this problem together and call it a day.
Thank you. Okay. Oh, I'm really confused. I don't know why.
On this problem?
Yeah.
You don't know why?
No.
I don't know. Let's. All right. So what do I have? Well, I clearly have a sphere that is radius 2, but that sphere is not at the origin. It's lifted up, and I can calculate. Actually, I can't calculate anything here. Yeah. So I don't know where the center is. I don't know what this, according to the problem over here, I don't know what this location is. So I can't really work out the angle phi. And if I can't work out the angle phi, I can't set up the spherical integral. So we set up cylindrical integral because this is cylindrical. This is going to be dz r dr d theta.
That was why.
You got it? And then what do we have? We have z for the top. Z for the top is root 29. The bottom is the square root of 4 plus r squared. And then we have r. R is, when we equal these two, we can find r. Right? So square root of 29 equals to square root of 4 plus x squared plus y squared. So it's 5. Right? 0 to 5. Because you square both sides, you get 29 is equal to 4 plus x squared plus y squared. And you move 4, you get x squared plus y squared equal 25. So that's the radius is 5. And then 0 to 2 pi for the full rotation for the object.
Okay, can you just explain the cylinder? How did you know this was cylindrical or not?
I don't have any information to figure out the phi. Phi is the angle, right, that goes like this. And I can't compute that angle. Of course, that's where you had the problem. Because that's where everyone should have a problem. Because as soon as you can't find this, you can't set up the middle limits.
Yeah.
And that's done. Yep.
So basically, it's like a lesson, like know when to use air.
Yes. That's it.
I just got the hat.